All right, so now that we've seen the concept of a flow map, it's natural to ask whether you can frame the idea of first integrals or constants of motion in terms of flow maps. Okay, so first integrals in terms of flow maps, and there's this concept known as the pullbacks, which we'll talk about. Okay, so if you recall, a first integral is a non-constant function, but it's constant along solution trajectories. A function that is constant along solution trajectories. So what that means, I should call this function I of y. Okay. So this means is that if you take I and you evaluate it at the initial point, y0, this is going to be I of y along that solution trajectory. But this I of y of t can be expressed in terms of the flow map, because you can write y of t as phi t applied to y0, right? That's really the definition, if you will, of the flow map. So I evaluated on phi t applied to y0, okay, is going to be I at y0, okay? So this is saying that I applied to y0 is equal to I composed with phi of t applied to y0. Okay, so this object here, I composed with phi of t, I'm going to write in the following way. It is the pullback of the map I by this map phi of t. Sorry. Okay, so this is how we write this. Okay, and this has to be true for all t and y0. Okay, so here, this phi of t star I is the pullback okay, of I by the flow map phi of t. Okay, and again, it's just given by this specific choice of composition. So you might ask, well, why is this thing called the pullback? Okay, so it's natural to talk about what the pullback of a scalar function is. So more generally, the pullback of a scalar function is defined by the following commutative diagram. Okay, so imagine you have a map from two spaces M to N. Let's call it G. Okay, and then on each of these spaces you have some scalar valued function. Let's call that I. Okay, it's scalar valued, and then I'm going to identify it's like these two copies of the rail. Okay, so the diagram basically just is completed by the following. Okay, so this map here, it's like from M to R, is the pullback by G of the function I. Okay, And the reason, of course, why this is called the pullback is because you start off with a function in the target space of the map G. G is a map from M to N, and you have a scalar valued function on N. Okay, so by making this diagram commute, what you've done basically is you've taken this function I, which maps N to the rails, and you've pulled it back to a map now from M to the rails. Okay, so it's called a pullback because the direction of the map is from M to N, and you're pulling a scalar valued function on N back to M. And it's easy to convince yourself that for this diagram to commute, what has to happen is that G star I, the pullback of I by the map G, is defined to be nothing more than the composition of I with G. Okay, so this is the pullback of a scalar valued function. One nice thing about it, it's like, which is again easy to observe, is that the pullback is defined. It's like even if this map G is not invertible. Okay, so again, it's once you have this language of flow maps, it becomes very easy to talk about basically first integrals. So a first integral is basically a function whose pullback by the flow map is itself.